technique that is used to reduce activity in the circuit, to reduce alpha, is a technique called clock gating. And the best way to look at clock gating is to think of this very simple case where the value of clock gating becomes immediately apparent. This is a case where we have a 64-bit register. So there are 64 flip-flops. You can see in this diagram only 4 flip-flops, but you have to imagine that each of those 4 flip-flops actually represents 16 separate flip-flops, which is what I'm trying to show with this number 16 here. This is a standard convention to show buses. So each of these flip-flops represents a group of 16 flip-flops, and you have a net width of 16 wires coming out here. So there are 16 times 4, 64 flip-flops here. And the circuit is such that there is an enable signal En, which you can see it goes to muxes. There's a mux at the input of every one of these 64 flip-flops. And the enable controls the mux. The enable is the select signal for the mux. When the enable is 0, then the flip-flop output goes back to the input. So you can see there is a feedback path here through the mux. The outputs of the flip-flops goes back to the inputs through the muxes. And so when the mux select is 0, the flip-flops don't change state because the output goes back to input. Only when the enable is 1 can the flip-flop change state, because then when the enable is 1, then inputs go to these flip-flops, external inputs come. When the enable is 0, the flip-flop simply recycles its output back to its input. So that's the kind of logic we see here. And you can see the clock is going to all these 64 flip-flops through a clock tree. The clock tree consists of a bunch of buffers. There's first a single buffer that fans out to 2 buffers, and each of those 2 buffers then spans out to 4 buffers. So you can see there is 4 into 6 and 1, 7. There are 7 buffers in the clock tree here. Okay. Let's look at the circuit as it stands. There is no clock gating here. And what I've shown is an enable signal that is initially high, and it goes low for a couple of clock cycles and goes back high again. So you can see the enable with respect to the clock. There are 4 clock pulses you can show here that you see here. During the 2 middle clock pulses, the enable is 0. In the first clock pulse, the enable is 1, and in the 4th clock pulse, the enable is 1. Okay. So when the enable is 0, the flip-flops don't change state. So in the rising edges of these 2 pulses, the 2 middle pulses, they do no work since the enable is low. When the enable is low, the flip-flops are not changing state. So even when the flip-flops receive those pulses and receive the rising edge of the pulses, the flip-flop does not change state. So there is nothing happening as far as state change is concerned during the 2 middle clock pulses. So even though the clock is pulsing, nothing is changing state. So those 2 pulses are basically useless pulses. If you did not have those pulses, nothing would happen. The circuit would work just as well. But every time there's a pulse, you're dissipating power. So you have some useless power being dissipated in this case. The 2 middle pulses are doing no work, but they're dissipating power in the buffers. Where is that power being dissipated, by the way? Whenever there are clock pulses, it's the buffers in the clock tree that are dissipating power every time there's a pulse, every time there's a clock pulse. And when you have useless clock pulses, which are not doing anything which are not changing the state of the logic, the buffers are still dissipating power when those pulses come through. So one idea we can consider is to eliminate those 2 middle pulses and therefore reduce the power dissipation in the clock tree. So we could change the circuit in the following manner. We'd remove those muxes at the inputs for the flops, and that enable signal that was going to the mux selects now goes to an AND gate instead. So you can see at the bottom here, that same enable signal is coming to an AND gate. And this AND gate has that enable signal as one input and the clock as the other input. Okay. So whenever the enable is 0, this AND gate output will be 0 and the clock will not go through. Okay. So here you still have the same enable signal. You still have the same input clock with the 4 pulses, that's right here. But at the output of this AND gate, I have a new clock called, I'm calling it gated clock because it's gated by this AND gate, GCLK, gated clock. And now in this gated clock, the 2 middle pulses have been eliminated because when those 2 middle pulses come in, the enable is 0. And so the AND gate does not pass those through middle pulses to the clock tree. Okay. So now you can see that on this clock tree, the activity has reduced. The number of pulses per second has become much less. The initial clock had 4 pulses. The gated clock has only 2 pulses in the same period of time. So the overall power dissipation in this clock tree, all these buffers, that power dissipation would have reduced by 50%. So we have simply changed the circuit from this mux-based circuit to a clock-gated circuit. The circuit functionality has not changed at all, but the power dissipation has come down. So this is the idea of clock gating. Now there's a problem with using AND gates for clock gating, and that you can see if in these waveforms here. So the idea we had was we replaced those muxes to which the enable goes with an AND gate on the clock tree, and when the clock enters, when the clock comes in, it goes through an AND gate which has an enable as the gating signal. Now, what can happen when you use a simple AND gate is shown in this timing waveforms here. What can happen that can make things not work properly? That's what I'm trying to show you. So let's say that enable signal happens to change state when the clock is high. So what you see here is there are 4 clock pulses. The enable initially goes from high to low when the clock is low. Okay, so it's going high to low when the clock is low, and then the enable remains low, and then it changes from low to high when the clock is high, and again goes high to low when the clock is high. Then what happens to this GCLK signal? So that first pulse of the clock goes through because the enable is high. The second pulse of the clock does not go through because the enable is low. And the third and the fourth pulses of the clock, they cannot get clipped because when the enable goes high, or whenever the enable changes state when the clock is high, then you will have these kind of glitches at the GCLK, right? You can see that here because when the clock is high and the enable goes high, then both the inputs to the AND gate are 1, and the output of the AND gate will go to 1, which is what you're seeing here. And similarly, when the clock is high and the enable goes high to low, the clock will also go high to low. So you'll get these very spurious or very incorrect clock pulses at the output of the AND gate. Essentially, what's happening is when the clock is high, if the enable changes state, then there will be a transition at the output of the AND gate. So the GCLK will see an edge. There will be an edge at GCLK. And that edge at GCLK will create these sort of wrong or incorrect pulses on the clock. So this is a serious problem with this simple idea of using an AND gate for gating clocks. And the problem is that when the enable to the AND gate changes state when the clock is high, then we have incorrect pulses at the output of the AND gate. One thing we could do is to somehow design the circuit to make sure that the enable never changes state when the clock is high, and that is one option one could pursue, and in principle that can represent a design style. That adds a lot of burden to the design. You have to make sure that the timing of the enable signal and the clock signal is so correctly aligned so that the enable never changes state when the clock is high. That becomes very difficult to implement.